For many of you, kombucha is a tasty carbonated drink. It's good for cooling down on a hot Arizona day and bonding with your friends. But it's even better for your gut health. The process of making kombucha, fermentation, fills the beverage with bacteria, antioxidants, and acids that support a healthy gut microbiome and aid digestion. But did you know that the process of making this fun drink produces a byproduct that has the potential to reduce environmental pollution and change the leather industry forever? Hi, my name is Samantha Provenzano. I am the testing lead for this project. I'm sure many of you, including myself, own a wallet, belt, or handbag made from animal or synthetic leather. However, the production of these popular products has a major problem: negative environmental impacts. For example, leather produced from cattle contributes to 10% of global carbon emissions, 20% of global wastewater, and 35% of marine microplastic pollution. To combat these effects, companies produce synthetic leather. However, they can include plastics like polyurethane and polyvinyl chloride, which are not biodegradable. In a time where it is more important than ever to combat climate change and global warming, it is important to create products that have minimal environmental impact. That is where our project comes in. When kombucha is fermented, a series of reactions produce symbiotic culture of bacteria and yeast, SCOBY, which is a biofilm of pancake-like layers comprised of cellulose filaments and microbes. For this project, we seek to outline a cost-effective manufacturing process to produce textiles out of kombucha SCOBY as an alternative for current leather products.
Hi, I'm Zoe Johnson, the experimental lead for this project. For our experiments, we chose to test several different chemical treatments for the SCOBY based on a review of literature. We tested glycerol and coconut oil as possible treatments that could improve the physical properties of the SCOBY. Further, we treated the SCOBY with NaOH and sodium bicarbonate to reduce the natural acidity of the SCOBY, but we ended up eliminating the use of NaOH after discovering sodium bicarbonate was sufficient to neutralize the pH. Throughout our experiments, we continually sought ways to improve the safety of our process and minimize the environmental impact. We also wanted the SCOBY to have a pleasant texture, a neutral smell, and an attractive appearance to make it appealing to a customer base. To improve the physical appearance, we tested natural dyes made from coffee grounds, hibiscus flowers, and butterfly pea flowers. We initially experimented with using hydrogen peroxide to bleach the SCOBY before dyeing, but we found that it did not improve the uniformity or the physical appearance. We initially ran experiments in which we tested each treatment individually. In these experiments, we found that glycerol improved the strength and the abrasion resistance, and coconut oil was effective for reducing the hydrophilicity. Then we ran one final experiment using sodium bicarbonate, glycerol, coconut oil, and the hibiscus and butterfly pea flower dyes in different combinations to choose our final treatment process. We conducted a variety of physical tests inspired by ASTM standards to quantify the performance. To test the abrasion resistance, each sample was rubbed with a piece of sandpaper and the weight loss was measured. To test the physical strength, we folded each sample until it broke, or until 1,000 folds was reached. To test hydrophilicity, a sessile contact angle test was performed. And to test absorption, each sample was placed in DI water and the mass was taken before and after. In addition, a qualitative survey was conducted to gauge public opinion on texture, smell, and adherence. Our final SCOBY treatment consists of glycerol, sodium bicarbonate, natural dyes, and coconut oil, which performed best in the physical tests for strength, abrasion resistance, and hydrophilicity.
Hi, I am Rohini, the process design lead for this project. For the process design, we modeled a SCOBY chemical treatment process as an addition to an existing kombucha production facility. We estimated that the facility had around 20 fermentation tanks with around a 10-day fermentation time, meaning around 2 SCOBY per day, or 730 SCOBY per year, were inputted into our treatment process. The treatment process consists of a series of chemical treatments followed by drying. Based on the results from our experiments, the optimal treatments were sodium bicarbonate, glycerol, coconut oil, and hibiscus and butterfly pea flower dyes. For the sodium bicarbonate,
glycerol, and natural dyes. Around 1,900 liters of treatment solution is pumped from their storage tank into the main chemical treatment tank. The SCOBY is then lowered into the treatment solution via a gantry tank and submerged in the treatment for 30 minutes to an hour, depending on the treatment. Once the treatment has concluded, a portion of the chemical solution will be pumped to waste, while the majority, 80 to 90%, depending on the solution, will be pumped back into the storage tank for use in a subsequent SCOBY. This treatment recycling scheme was implemented to reduce feedstock waste and also reduce processed water consumption. Then, the SCOBY will be rinsed to remove any excess chemical and reduce cross-reactivity with the SCOBY in any subsequent treatments. This will be repeated first with the sodium bicarbonate, then with the glycerol, and then with the natural dyes. Next, an around 1 millimeter layer of coconut oil will be topically applied on the SCOBY, where the SCOBY is placed on a very slowly moving conveyor and a slot die coating mechanism deposits the coconut oil on top. Finally, in the last step, the SCOBY will be dried on a batch dryer with a fan to provide convective flow. Mass transfer calculations estimated a 16-hour drying time, where around 95% of the SCOBY mass is evaporated out. After this, we have our final SCOBY textile.
Hi, my name is Grace Tofter, the implementation lead for this project. Overall, we were able to develop a cost-effective process for producing vegan leather from Kombucha SCOBY. Over a 15-year operational period, we have a net present value of $287,000 with an investment rate of return of 31%. The product meets key material property goals while also demonstrating strong potential for scalability and integration into existing kombucha production systems. By using SCOBY as the base material, we are able to repurpose what would have otherwise be discarded into a functional product. Our process incorporates natural dyes, such as hibiscus and butterfly pea flowers, which reduce the reliance on synthetic dyes and further lowers the environmental impact. All the chemicals used in the process are biodegradable, non-toxic, and environmentally friendly. Further, we implemented a treatment recycling scheme to reduce processed water use and waste. Looking ahead, there are several opportunities for future work. Continued experimentation with alternative chemical treatments could further enhance material properties. In particular, exploring substitutions for glycerol, which was relatively expensive and required higher concentrations, could improve our alignment with our cost and sustainability goals. Additionally, addressing issues with the uniformity of the SCOBY could make the final product more commercially viable. Finally, our current process is batch-based and has a high labor cost. Future work could focus on developing process automation to streamline production, reduce labor requirements, and improve scalability. Overall, our results demonstrate that kombucha leather has strong potential as a sustainable material, and with further optimization, it can serve as a viable alternative in the future of eco-friendly textile manufacturing.